Yes, so we have welcome back, guys. We still want to continue with our physics lectures, and we're still on the practical part of physics. And my name is Samuel D. Koidia, and I want to also admonish you, advise you to actually follow up this program much more by subscribing to this program as we go. Now we have the angle of minimum deviation and triangular glass prism. Our previous video was on the rectangular glass slab or glass prism, and we were able to identify the refractive index, and also we were able to also measure the latigal shift of the lines on as we were doing that experiment. So now today we want to look at the angle of minimum deviation of a glass prism. As usual, I'll first of all explain the principle behind it. You know, Newton was very key here. Newton took this material, the triangular glass prism, and that was how he was able to expose the colors of the white light we talk about here as sun. The sun is having constituent colors, and those colors were exposed by Mr. Newton using the triangular glass prism. So the prism also serves as a refracting medium and dispersing medium. So here we're going to see two things happening. The ray of light is going to be refracted, and at the same time it's going to be dispersed. So we're going to have dispersion and deviation. So when it's dispersed, it will deviate from its normal or incident direction. So now let's go with that. We are given a triangular glass prism in this case. So let's have a triangular glass prism there. So now in the exam or whatever thing you're going to do with these experiments, you will be required to first of all draw an outline. And as usual, I have a couple of materials here. We have the triangular glass prism. You can see it's a kind of triangle, and it has a rectangle somewhere here, and there is another rectangle somewhere here. And you have these rectangles, you have three of them, and you have a triangle somewhere there. So it's a transparent material, so it's a glass prism. This is triangular, so we call it triangular. So now we have a couple of definitions to do, or description to do here. We want to find the refracting angle. The refracting angle is defined by the point where the ray is entering and where you are observing. So if I'm observing, I'm putting the incident ray is coming through here, I'm observing this path, then this angle becomes my refracting angle, or the angle of prisms. You can call it that way too. So if the ray of light, it's like I want to now find the normal here, I draw the normal. As usual, you can also draw the normal there. So you can, let's say I want to draw my normal somewhere there. I got the normal here. I have my 90 degrees somewhere there, or because of space I can go the other way still and get my 90 degrees somewhere. So my 90 degrees, this tells me that this is my normal. So I can go with that line there, it gives me the normal. So let's see there, that is the normal for this. So here, this is the normal. So I've got the normal there. So with this normal, this is always 90 degrees. And as usual, you will be also given a set of angles. So let's go back to those angles again. Or you have angle of incident measured in degrees, maybe 30 again, 40, and so on. So you have those ones, and you will be asked to find the. In this case, we are going to focus our attention on this much more. So we will be asked to find the angle of deviation as the ray of light deviates from that stuff. So we'll go to that thing again. So we have the normal so far. So on this normal, you'll be asked to measure the angle of incidence. Remember how we measure the angle of incidence the other day? So that is the same procedure here. You can measure it this way. If you want to take it from the 90 degrees line, you know that if I go 30 degrees that way from 90, I have to go to 60. That gives me the 30 there. So I can go the 30 that way there. Yeah, you can still go that way, or you go straight this way and you get the 0, 10, 20, 30. So I got 30 somewhere here. So after putting it right there, I ensure that this my normal is on that line. Then this is 10, 20, 30. So this is 30 somewhere there. So I connect the 30 onto that junction. I have my, so let me just be drawing them habitually because of yes, let me use this. So I got that line here. So what is exactly what you will be doing on your drawing paper. So you already have an idea on the drawing paper. So let me say I have 30 degrees somewhere there, and that is the incident ray. So on that same incident ray, so you now make sure you space at least 4 centimeter space between the pins, 4 centimeter there and 4 centimeters somewhere there. So let's say I have the space here as P1. I put my pin here and I put the other pin somewhere here, P2. So I've got the incident ray and the 2 pins P1, P4, P2. Those are the object pins. Those are the ones I'm going to look through the prism to discover their images as they are moving. So I'll be able to discover to actually define the refracting angle. I said the refracting angle is the angle formed by these two phases where the ray is entering and where the observer is looking through. We are looking through AC. And this is how the ray is entering. So this angle here is going to be the refracting angle. If I was allowing the ray to enter here and I look through here, then this one becomes my refracting angle, the same as we go there. So now we've got the normal. So we put 2 pins there, put 2 pins somewhere there, and by looking at this part of the block, because we say these are refracting angles, so we are looking here, we are supposed to put 2 other pins. So we put 2 other pins such that, as usual, you know, the light in that vicinity will drop on this object, and these pins will send the ray of light from this pin will enter this block, and because it's transparent, it's going to obey the same law of refraction. It's going to make sure it's bent towards the normal, because its light is moving from optically less dense medium, now it's entering a denser medium, so you expect it to bend towards its normal. This is a normal, and vice versa. If it's moving from optically denser medium to less dense medium, it move away from your normal. So watch what is going to happen here. The ray of light entering from the air into the block will bend towards the normal. So these 2 rays will produce their images somewhere here. So you see the images of this here and here, or somewhere there. So let's say here and here. So what you're supposed to do as a scientific investigator, so we are going to assume that you want to investigate what happens to the ray when it enters inside here. We say the theory says it's supposed to bend. So let's see what bending that is going to take place here. So you now put 2 other pins here and here with the same one eye closed, such that you avoid parallax. You're going to put 2 pins there and there by closing the one eye so that it gets the parallel here. So now you see that the images of these 2 pins here and here, as you observe them inside this transparent medium, must correspond with this point and these 2 pins you are putting. So let's say these 2 pins were here and here. So I've placed the 2 guys here. This is P3 and P4. So I have placed these 2 pins here, P3 and P4. The distances between the pin is not important. It is this distance between these other pins that are very important, because they are the original ray coming from. So now we have this ray, so you now connect the 2 together. Now we say remove the pin. We go by the instruction. Now you have done the incident. You have placed 2 pins on that incident. The incident angle was 30 degrees. You place 2 pins there. Now I say remove the pins. Look through the face AC. Locate 2 other pins, P3 and P4, such that the images of P1 and P2, as you see them inside this block, appear to be in straight line with this P3 and P4. So that's how we have already identified the P4 position and P3. So now we are supposed to remove the block. So that was the block in there. Now we remove the block from that layout. When we come to demonstrate, you see that. So now I say connect these pins. So you connect these points. So you remove the block, remove the pins. Now you connect this. So we are trying to connect this. So when we connect these 2 pins, these 2 points, we'll have, let's say that is where it is now. This is, yes, so now we've got those 2. So we have seen that this ray of light has moved. Let's say here. Now let me use this part and this part, because I'm not measuring it. When we get to the point, you will see how it is being measured. So I got it there. See here, be precise. So this is my P3 and P4. So I've connected that. So now I move this, I connect this to this, because you expect this ray to bend. So it's supposed to bend somewhere. So it's supposed to bend, it has bent somewhere. Let's see that. When we go do it on the thing proper, you will see the difference there. So there, this I'm just writing arbitrary length there. So we expected it to bend, of course, because it's bending towards the normal. It is supposed to bend towards the normal because it's moving from optically denser medium here, entering a denser, optically less dense medium to a denser medium. It's supposed to bend towards the normal. So let's assume it has bent through that stuff. So now it's bending, and that's the emergency. So I have to draw a normal somewhere there. I draw a normal somewhere. You know how to draw a normal to a face already. We've repeated that in the previous videos. So that's a normal. So I draw that normal between the two. So let's say I have a normal there. So this angle becomes the angle of emergence. You know that already. But let's assume that this ray did not pass at all. This ray did not deviate at all. It was supposed to go straight there. And this other one too was supposed to go right straight. Because if there was no block, it was supposed to go right straight there. So that is the ray. Let's say it continued. This incident ray continued there in that direction. And this refracted ray came this other way, so it ended up here. So there is going to be a deviation. So we have already seen what has happened to the ray. Now it's deviated from this incident part. It was supposed to go straight, but because it entered a block where the block is optically denser, it changed the speed of the light, and the light has to bend. So it bent towards. So now we have a refraction here, angle of refraction, because there's going to be double refraction here. Let us see, let's name this as refraction 1, and now this, yes, let's say that. Now we have another refraction taking place here, and this refraction 2, refracted angle 2, now becomes the incident angle in this case, because there's a normal somewhere there. And now you can see that there are two places where the ray is going to be deviated. It has deviated here. That is the deviation there. Now it was supposed to go straight, so it has deviated here too. So there is a deviation from its incident path. That's the one here. Let's call it deviation 1. And if it was supposed to go straight, it also deviated. So it deviated again too. So there are two deviations here. The ray was supposed to go straight, but it ended up bending. So it has deviated from its incident direction. That deviation angle is D1. Alright? But when it also entered the block, it wanted to go out of the block. It's moving out of the block. It's moving from optically denser medium to less dense medium. It moved away from the normal. So it was supposed to go straight there, but it deviated. So it has done another deviation here. So the ray of light has deviated twice. So now this angle here is the same as this angle, if you look at this properly. So this is vertically opposite angles are equal. This angle is equal to that. So now if I should take this, let's call this point Z here. If I should take this shape outside, you can see that I'm going to have a triangle there. That is Z. This is, let's call here O. That's O. And let's call here N. So I have N somewhere here. So I have got D2, and I've got D1, and I've got D here. But if you know this geometry, you must have discovered that sum of opposite interior angles of a triangle must give us the exterior angle. So D is equals to D1 plus D2. So let me come back to the principles here. See what happened. When the ray of light entered this block, it bent towards the normal, trying to obey the law. So now when it was going out of the block also, it's supposed to move away from the normal. So it decided to move away from the normal there, because it's now moving from denser medium to less dense medium. So the ray of light has deviated twice. It has deviated here from its incident direction. That was its direction, but it ended up this way. So it has deviated DI. Now when it moved inside the block again, as it is going outside to the air, it also deviated again. That is moving away from the normal. So instead of going straight, it has deviated this other angle here. So there's second deviation here, there's first deviation here. So first deviation is inside the block, the second deviation is outside the block. So now we have connected this angle to be equal to this, because we have vertically opposite angles are equal. If this is D2, so D2, this angle also must be D2. This is vertically opposite angle. This distance is equal to this angle. This angle is equal to this. Vertically opposite angles. And we know that already. Now we have already investigated the two. So we also have we also know that this angle is also going to be vertically opposite to this R2. So R2 is vertically opposite to this. This one is equal to that because there is another refraction here. So this is R2 is vertically opposite to that. D2 is vertically opposite to that. So that's how we're able to get these two, D2 coming inside this triangle. And here, we also looked at it here. We now want to look at the incident angle. It's a summary of the two of them. So watch that. So you must know this geometry here. And you must also know that angles in a quadrilateral must give us, so let's call this point P. So I put another angle here, I call it theta. So now if I should bring that triangle out, A, P, N, and this is A, this is O, this is P, and this is N. So I'll have the angle of the refracting angle, that's A, we know that already. Now we have here, I've labeled here as theta. Now you know that this angle is supposed to be 90 degrees also. This one too is on 90 degrees. So there is 90 degrees there, there is 90 degrees there. So now I've taken this, and this. It's a 90 degrees somewhere there. So now I'm connecting the two together. So we now have A plus 90 plus 90 plus theta is equals to sum of angles in a quadrilateral is 360. So now we have A plus 180 plus theta is equals to 360. So if I remove that, so I'll just shorten it because of the time. This is 180. So here I've got this equation. I keep that equation. So if you do the math here, you know. So now this is one equation also. This is another equation. I keep this equation. Yeah, so now this one equation, this is another equation. Now I can now look at the triangle that is down. There's a triangle down. This is for triangle that is OPN. This is refraction R2. This is refracted angle R1. This is this angle and this angle. And now that was the refracted ray that was going. So we have NPO, and we have here as theta. So I can do the math there as well. We can now say, therefore, R1 plus R2 plus theta is also equal to angles in a triangle. So we now have R1 plus R2 is equals to 180. Then we drop that also. That is 180. Another equation. Then we call it equation 3. Is okay. This is equation 1. Let's say equation 2. So I've got equation 3 in that form. So we have two 180 here. So since this equation equals to this, so I can say equation 2 is equals to equation 3. So equation 2 is also adding up to 180. So we now have A plus theta must be equals to 180, and R1 plus R2 plus theta is also 180. So I can say R1 R2 plus theta is all equals to 180. So this equation equals that equation because this is 180, this one too is 180. So now I drop these guys here. I'll have A is equals to R1 plus R2. So I've got a major equation here. That's a very major equation. So I keep it that way. So now we go with this. I'll come back to this incident angle. So if you check the incident angle, you have a line here. So you have a line here. That's incident angle. So at this point O, you have this ray coming. This is the ray. This is the incident angle I. As this is equals to D1 and DR. So you have D1 and DR and R1. That is, these two angles equals to this incident angle. That is, the vertically opposite angles are equal. So vertically opposite angle, you can say I is equals to D1 plus R1. So I can keep that equation too. So I can do the same for the angle of emergence. The angle of emergence is there. So this is N. And the two lines coming, this is D2 and R2. This is D2 and R2. And this whole angle is angle of emergence. So now I can say vertically opposite angle E is also equals to DR2 and D2. So I get that equation too. So now I can make D1 the subject of the formula here. D1 is going to be I minus R1. So I can keep that. I come here also, I can make D2 the subject of the formula. D2 is equals to, yes, so now you have defined D1 already. So we have defined D1 as equals to, this is I minus R1, and we also defined D2. D2 was E minus R2. So now we come back with the major equation 1. So from D equals to D1 plus D2. So we can substitute. D is equals to, now this D1 is I and R1, and D2 is E R2. So now we can collect the terms properly. So you have I plus E is the same as, if I subtract this, I'll have R1 plus R2. If you do the math, you clear these brackets, you get this on top, of course. So now we have already found R1 and R2. It was somewhere here. R1 plus R2 is E. So anywhere I see R1 plus R2, I put A there. That is the refractive angle. So I plus E is minus A. So I have minus A. Yes, minus A, somewhere there. So I transpose, I have D plus A is equals to I plus E. Right there. So now we know that. Now let's come back here. This angle of deviation is only possible when the ray of light that is traveling inside the block is not yet parallel to the base. So when the minimal deviation occurs, this ray of light, this ON, must always be parallel to the base here, BC. So that is the time you expect minimal deviation to occur. And when that happens, the angle of incident is always going to be equal to the angle of emergent. So at minimum deviation, the angle of incident is equal to the angle of emergent. And that at that point, the refracted ray is always going to be parallel to the base of the block. So you can watch out for objective questions. When do we expect minimal deviation to occur? That is when the refracted ray inside the block is now going to be parallel to the base of the block. That time you expect the minimal deviation to occur. So when minimal deviation occur at that point, I equals E. So anywhere I see E, I put I. So this equation is modified as I plus I. So I now have two I's there, and this is D plus A. So I can do the math properly there. You also go. So now you have D plus A is equals to 2I. If I want to make I the subject, I divide by 2. So this guy will go. So I have I is equals to D plus A divided by 2. So I have that. So now if I'm coming back to the Snell's law, remember it's T block. We are directing light moving from optically less dense medium entering a denser medium. Because it's moving from optically less dense medium entering a denser medium, it is obeying the law of refraction. Now one of these was the refractive index was given as sine I all over sine R according to the Snell's law. So Snell's law will now define this. So what is the I? So it is N is equals to, we have sine into, instead of that I, and now since I found that it's going to be D or A plus D, that's at minimum deviation. So I differentiate now. It is only at minimum deviation that the incident angle equals the emergent angle. So I differentiate that. This is it there, and I come with sine R. But sine R, we know that when the angle of refraction is always going to be equal to twice the angle of the refracting angle is equal to twice the angle of refraction. So if I divide here by 2, I'll have that. So R, this R also now is equal to A over 2. So I put it right inside that equation, and I have sine into A plus D and all divided by 2. Then I have all over sine A all over 2. So this is another equation from the refractive index of glass when you use the deviation method, that is minimal deviation method. Now you can now continue with this, which you can do for 30. You must have measured this angle of emergence if you like, and you can also measure the angle of deviation. But here we are just interested in the angle of deviation. So how did I get that angle of deviation? Let's see, this is what happened here. So this is the Z, so you are measuring this. So you now put your protractor. Let's see how you measure that. You put your protractor that and you measure that angle as it is done that way. So let me see. Yes, I can go this way. So I got this. Yeah, so you make sure this line is there, and now this other line you try to get it clear, or you get this way. So there. Okay, let's go this way. Now let's move it this way. Yes, we can go this way because we are trying to measure this angle. We can put it this way, and this line will give you that angle of deviation. That's where you measure this angle of deviation. So if you are using your protractor, you can bring it this way. It's easier that way. When you use the protractor, it will help you out. So you now put it right here. That is the normal, that is where at the junction, and now you read this angle here, so it will give you the angle of deviation, and the smallest of it is what is called the angle of minimum deviation, and it will only happen when this refracting angle is now parallel to the base of that stuff. So now this is the experiment for you. So let's come back to the we have got this now. So you'll be giving series of incident angles, and you do the same and try to find the angle of minimum deviation or angle of deviation, but there is a particular number that is going to appear in your reading, which is going to be the smallest of all, and that smallest of all only happen when the refracted ray is now parallel to the base of this prism. So you now get that value. That is going to be the minimum deviation. And now if you do the experiments individually, you find out that you have yes, values like if you read it from your equation, you can get, let's say, 40, 50, let's say 50, 55 even. You can mix that stuff over there, and you can see that the angle of deviation, these are the purported angles that you get when you do it on the stuff there. So you just have 39 there, I'll have 38, and you have 39 again, 39. So let's say another 39, and you have 40. So you can see that there is a link here. There is something happening. These values, if you do it correctly, you're going to see that it keeps reducing up to a minimum value, up to a minimum point, then it keeps increasing. So if you draw that graph, you are going to expect something like this on the graph. So let me just tidy up some part of this equation, this blackboard. So we see this whiteboard, and we see how we can experiment that. So now if you continue, you use angle of incident, you are approximately going to get something around 48, 40. It could be plus or minus 0.1 or point or minus 1 is possible here. So but you try as much to also perform that on your own, but you get numbers and the minimum deviation using an equilateral triangular prism, that is 60 degrees. When you use that, approximately with these angles, you get numbers closer to that, and you have 40. Let's get that. These are expected values, let's say. So now you come to draw. If you draw D against I or against emergent, it's possible that you can also find the angle of emergent is possible. So you get that is against I, you drop, you find out that you have if you plot, you have, if you go through this, you see, I'll just give you a sketch. Let's say the smallest of all of them there is 38 degrees. So this 38 degrees now give us the minimum deviation. This is a minimum deviation. So the angle of minimum deviation is 38 degrees. Yes, from that experiment when did it in the lab with this glass prism. So now that's, after drawing this, you now take the point where the lowest point of that curve, which is the minimum, that is the minimum deviation, that's the smallest of all the deviation. So if you put it inside this, you'll be able to find the refractive index of this block also using this formula I've just discovered here. So let's see, the minimum deviation is 38 in this my diagram. That is what you're supposed to get in the lab if you go through this. And these are the values I got when I did it independently. So you also use the same angles and see how you get there. You may deviate from one or two point there because we are not the same human being, but I think you can get close to these numbers as we go. So we put it right here. We have numbers. This is the refractive index. Inside this equation is now going to be sine into, this is a glass that was equiangular, so it's 60 degrees, plus the deviation angle which I've got, which is the minimum deviation from that my equation or from my values. I'll be able to plot this out there, and if you even plot it against the emergent angle, you will still have the same shape there. So somehow we have, this is dm, then that dm is now 38 from my experiment. Yeah, you could have a different number. It's possible that you have a different number, but I got that as 38, so divided by sine of 60 divided by 2. So you can have, this is 98, this is 98 by 2, so this is 49. So you have sine 49 divided by sine 30, sine 30, that is the incident, the refracted, the angle of refraction, or the index, the refractive index to be precise. So have n is equal to, if you punch this on your calculator, you get something around 4.5. So if you round up that, maybe you can get something that is this is 1.5. So you can punch that from your calculator. Now this is how I told you, the whole experiment is for you to get this number. This number is the minimum deviation, dm. So if you get the minimum deviation from all, you must know how to read this here. When this line is projected, it is this line that is projected to form this angle of minimum deviation. So if you can look at this structure again, so that you see which angles you are trying to actually measure. So watch, if this ray was supposed to go straight, it was supposed to go in that direction, that is, this was supposed to go right there, and but it ended up coming the other way. It ended up this way. Yeah, that is this ray. Yeah, it started this way but ended up there. So now it has deviated. That is the angle of minimum deviation. So how do I measure that? It is to project this to meet this point. That is the point I'm trying to define here. That is a z. Then this other line goes right straight there. So this angle here is what you are measuring as the angle of deviation, and the smallest of it is what is called the angle of minimum deviation. So you must be able to do this experiment on your own now. You'll be changing the incident angles. In the examination, you're given different angles and you try to actually get the curve, but this is actually the curve you get sometimes if you are plotting it against this. So normally, when I did it with the angle of emergence, if I did that, I discovered that that's just when I drew the angle of deviation against the emergent ray, emergent angle, I also got an angle, a shape like this, and when I read this was 44 degrees, but this also corresponded with this. So that's what I said there. At a point when this equal, so you must be able to get the angle of deviation and the emergent angle becomes the same somewhere there. So if you do this, you get that stuff there. I was able to get this value. So try as much to also go to the laboratory now and use this information and you plot this graph. Where our interest is this deviation we are trying to find, but you can only get it from series of angles here and finding the deviation, and the smallest of that is what you plot on your graph, and you'll be able to read this part of the graph. When I read it, I got 38, so, and that's the smallest from that. If you put it inside this equation, it must be able to give you the refractive index of this. So let's come to the block now and try to demonstrate it. Now we want to go, all what I've said there, we can demonstrate it here. First, we get the outline. The outline is this. We now draw the outline first. The question will say draw the outline. So we've got the outline of the block. So drawing the outline is just the perimeter, if you like. You just pass the pencil right around that shape. This is that. So I'm looking through, I'm putting the pins here, then I'm looking through here. So my apex angle here, which is the refracting angle, becomes this one here. So that's this, my A here is this, because I'm putting, if I was looking at this two face, this becomes the A, but that is it here. That's it. So I've drawn the outline. Remember all the setup, we have done this once. So you have the drawing paper, you have the drawing pins, the drawing board. So I assume that you know all of this. So now we have, so I remove that block. Say remove the block. So I remove the block. Now it says draw a normal. So I can draw a normal there with my protractor, as I did over there. I can draw the normal. They say I want to get the normal somewhere there. So I use the protractor and make sure that pin is somewhere there, and the line is just on that. That is exactly there. So the pin is there. So I got it on that face. This is the line on that face. So it says draw the normal. So I have the 90 somewhere there. this is 90. So now 90, I draw a normal right through. So there, that's the normal. Now on that normal, it says plot, puts there. I'm trying to put the, so this is at that point exactly. So I read 30 from my 30 degrees incident angle. So I'll go with it. 30 degrees incident angle. This is 10. This is 20. I have 30 degrees incident angle. So I have 30 somewhere there. So 30. You can get that. So I connect this with the 30 degrees. It's incident. So that is the incident here. So this is the incident ray, and on that incident ray, I said you ensure that you have equal spacing between the points. So let's say I have equal spacing there, equal spacing between the pins. So I have one pin somewhere here, another pin somewhere here. So now I'll take my pins, put it right here, put it right here. So I have placed those pins there on this, and these pins are upright. Ensure that they have reasonable equal spacing, and they must be upright. So now I've got that. Now the question will tell you to replace the prism back inside. So I'll come back and replace the prism right in there, So remember, this my angle was 30 degrees already there, so I replace it back inside. This is one precaution that is very important, that is to ensure that you replace the prism back inside its outline, because the moment it's not inside the outline, all your angles will be wrong somehow. So now you looking at the face AC. So I'm looking at this face AC. You see, by parallax, ensure that you put two other pins, somewhere there and somewhere there, such that the images of these two pins as seen inside this prism appears to be in straight line with these other two pins you are putting. So now I'm looking at these two pins will form the images somewhere there. So the image is there. So I can now look at this face somewhere, and I try to put two other pins. Yes, two other pins there, such that they appear to be in straight line with the images of this. So this is there, and we have the other one. So these red ones, these red pins are the ones that are going to be in straight line with the images of the two pins as viewed inside the block. So now I've seen that the two of them are, so I can't even see the green again because they are in line now. So all four of them are in line. The images of those two and these other two red pins there are all in straight line. So you want to observe that. You can just look at it there. So you can see that if you watch through, you will see that you see the image of the, if you watch through keenly, you will see that there is these two pins, and the images of the green are all in the same line there. As you watch it there, you can see they are already in the same line. If you go through, you see right there, they are all in the same line, because these two, they pass all their images inside, and the images of these two as viewed inside the block are in the same line with this. So you have now verified that it is already in line. That's the same thing there. If you want to watch it there, you see it's all in straight line. So you can verify this several times before, when you're convinced that you get it. You watch through with one eye so that you see that it is right in there. So you have these two pins and the images of these two as viewed inside there in that order. So that is how you have found the deviation now. So we come, the question will tell you to remove the block. So you remove the block, and now it says remove the pins as well. Now remove all the pins. It says join the 2 points. So the 2 points that I place were pins this and this. So I join the pins together, the points. So I'm trying to draw the outline properly, so for the edges we are not too sharp. Yep, so now we've got that. Now it says join the 2 pins, so I'm joining this pin and this pin somewhere there, so I join the 2 pins. Yeah, so there it's 2 pins somewhere here. So that those were my 2 pins there and there. Now it says draw another normal, so we come back and draw a normal at that point. So I draw a normal there. This is a normal, so you know how to draw a normal already. That is the, and you put it right here. So here now you have your 90, so I can draw my normal somewhere here. So I have normal, this is normal. Yeah, so this normal, and the normal is always 90 degrees with the block, with the face of the prism. So now we have to project this. We project this one backward such that it meets that incident ray at a point. So it's going backward there. Now I project this one too such that the two of them meet at a point. So now you can see that let's say this is the line. So it was supposed to go straight without no block. It was supposed to go straight. So now it ended up deviating, so it must have deviated at some angle. So it deviated at that angle. So let me place it again somehow. So it's this is the normal, and I have, let me just clean this one and make it a little bit proper for you. So now we have, yes, I want to see the normal properly. So I got it there. So it's possible that you can have my ruler was not too straight, but I can do that again. So I put the pins right in there. Put the pins right there. Yes. So now you use the same 2 pins. I'm repeating it again so that you follow up properly. So there we have the red pins. I put the red pins over there. Yes, I place back the blocks inside in the outline. Yes, place back the block. I want to just verify that reading again. See? Yes, so place it back inside. You can always verify and see. So now you put 2 other pins. See, I use the green pins again. So there. Now so wash it through there. Yes, that is there again. So we have the same point somewhere there. Yeah, in the first instance my hand shifted the block a little bit. I was saying that somehow I have them right in there. So I have this point and I have this other point. Yeah, so they appear to be in line again here. So the block shifted in the first case, the block shifted away from the outline. Now it is in the outline. So now there you can see that the 2 pins and this other one, the images are all in line, the same straight line. Yep. So now you always have to ensure that the block does not shift. So when you are drawing when you're observing, the block was out of the outline anyway when I was watching the first one. That's why I did it again, so that I now get the proper program there. So that's it. So I remove the block, then I remove the 2 pins. So I remove the 2 pins. Now the 2 pins are now here and here. So I remove these other ones here. Then I take my ruler, I project them right there so that I have this. Yeah, so now it's there. This is it. So I have moved the normal. Now you can see the normal has moved. In the first case it was the normal, the pin moved away, so that's why this line was bent, because I removed the block. It's possible as you are shaking, the block will shift, and you are watching, you will think you have placed it properly, and it can happen during the exam also. So you take your time and you see what happens. So that's it. Now I have drawn the normal. It's meeting here, so I draw the normal from that point. Let's see here. Right, so I've got my normal 90 degrees from that point. Here is still 90 degrees. So I get there, got to go very fast now. Now we have this normal, so that's it. The normal is there already. So now we have the angle of emergence somewhere here. So that angle of emergence is the angle I explained in the board. So I'm just trying to particularize all of them now. So now we have got the angle of the angle emergent ray somewhere there. So you connect this. Let's assume that there was no block. So this ray must have moved this way. Of course, it was going to go straight there. That's the ray here. This is the one. It was supposed to go right straight if there was no block, but it ended up bending to that, so it came up this way. So this is now the angle of deviation. That's the deviation angle, because so we move that. It ended up this way, so it must have deviated from its incident direction. So now you have this. So it ended up that way. So it has deviated from that angle. This is angle of deviation. So that small angle here is what you're supposed to measure. So you just put it here. So the angle of minimum deviation can be measured from that point. So let's see how we can place this protractor somewhere here. So you see, I'm making sure I put it right on that line. So it will give you the angle of deviation. So this is right on the line here. So I'll go measure here. So that is so I go through that. Then it was done. It was somewhere around 48. Yeah, that is almost 48. This is now I have 47.6. So I have 47.6 in this case. Yes, so almost 48. So now I have there 47.6 in this one is 10, 20, 30, 40, 47.6. So I have 47.6. So approximately 48. So you just have 2-point deviation there. When I did it with the other block, it was just the same. So now we have 47. We are there approximately. So now this is 48 or 47. This plus or minus 1 is possible. So you get this deviation here. So now seeing how we deviated, we found measure the angle of deviation. The angle of deviation is measured there. So you can put it right here and see how it is measured. So see, I'm trying to put it here so that I can measure it. So I make sure this one is there, then I measure that angle. Or let me use the bigger protractor here. So this is the same here. I make sure this junction is right there here. You see, it is this angle you are trying to measure, this angle that is coming around here. So this is it. Here I put it right at the Z, then it will give me this angle. That's the deviation angle. So this is from all here is the deviation angle. So you place your protractor just at the junction here, and because this is the line going straight, so that line goes straight, that's it here. And now if there was no block, this is the incident ray, it was supposed to go straight there, but because it entered that block, there's optical density difference, so this guy bent this way towards the normal. So now it ended up this is the emergent ray. So that emergent ray going there has deviated that ray by this amount. So that's how you measure from there up to there, gives you the angle of deviation, and the smallest of it is what we call the angle of minimum deviation. So you have seen the experiment so far here. Now this is the trace. You attach this trace onto your work and you'll be able to complete. So if you do that, you are going to have values like that, and you'll be able to plot. Yeah, if you draw I against, you get 48. When you I against, so if you read here, you're going to have 48 somewhere here. But if you do D against emergent angle, you get the minimum deviation occurs at 44. That's what I did here. We don't have time now to go through, but if you go through it consistently, you find out that you have all of this. Just change the incident angle like I did. So these are the values I got when I did, but it's for your own practical exercise. You try to also do the same and see how you can get. It's possible that you can get 1 or 2 degree difference with mine. So you try as much to do it. This is the triangular glass prism, the investigation of the triangular glass prism, and we always have the key points I want you to note. Anytime the angle of minimum deviation is achieved, the refracted ray is always going to be parallel to the beam, to this base of this and watch out for the angle of refraction. This is the refracting angle, or the angle of prism, if you like. So now that is the experiment for you. So I expect you to go use these angles now and draw your own graph and verify this point for yourself. I want to thank you for following me, and we continue this lesson again with some other activities on physics. So keep watching and subscribe. So that's it.